Here's the rumor that wouldn't sit down. What if everything, clusters hundreds of millions of light years apart, was drifting the same way, as if the whole pool had a tilt we couldn't see? Not a local nudge from Shapley, not the push of a nearby void. A current on scales the map didn't even cover. Alexander Kashlinsky and his collaborators had a way to check. Don't chase galaxies one by one. Listen for a whisper in the microwave afterglow. Hot gas in galaxy clusters scatters cosmic microwave background photons. If a cluster is moving relative to the CMB, it adds or subtracts a tiny bit of energy to those photons. The kinematic Sunyaev-Zeldovich effect. The signal is minuscule, buried under the CMB's own primordial ripples and a storm of foreground noise. But statistically, across hundreds of clusters, you can stack and filter. If clusters share a common motion, their KSZ fingerprints should line up into a dipole, slightly warmer on one side, slightly cooler on the other. Get this, they did the stack and claimed they saw it. A surprisingly coherent drift, several hundred up to roughly 1,000 kilometers per second, pointing roughly toward a patch between Centaurus and Vela. The press latched onto the phrase dark flow. It sounded like a hidden river. In talks, Kashlinsky's team pushed the implication. If the drift extended beyond where normal structure could cause it, gravity might be tugging from beyond our observable horizon. Maybe relics from inflation. Maybe something outside our cosmic patch. The idea turned heads because it punted past the guardrails. It dared you to think about what lay off the edge of the map. Meanwhile, desks filled with plots and skepticism. The KSZ effect is the quietest voice in a very loud room. You have to model cluster gas profiles, subtract foregrounds, choose masks to cut out contaminated CMB regions, filter angular scales, and hope your pipeline isn't inventing patterns. Teams lined up to replicate or refute. Some reanalyses found weaker hints. Others found nothing compelling. The word systematic started appearing in every paragraph. Did the filtering choices preferentially build a dipole? Were residual primary CMB anisotropies fooling the measurement? How robust were the cluster catalogs and their assumed profiles? Planck changed the tone. Full sky maps, higher sensitivity, better control of the microwave sky. When Planck teams applied their own methods, the case for a large-scale, horizon-busting bulk flow thinned to a thread. The claimed amplitude dropped. In many treatments, it vanished into the noise. A Planckiera null result wasn't just a quiet no. It was a statement that, within the instrument's reach and the models applied, there wasn't strong evidence for a universal drift beyond what lambdictum and known structures predict. Conference hallways got lively. Kashlinsky's group defended their pipeline, arguing that specific filters and cluster selections mattered, that Planck's null wasn't a generic death sentence for the effect. Others countered that if a phenomenon needs a particular set of choices to appear, you should get very suspicious. Rival analyses pointed at foreground leakage and profile mismatches. People drew arrows on whiteboards showing how a tiny bias at the filtering stage could leak a primordial CMB dipole back into the measurement and masquerade as KSZ. A micro story from one of those sessions. A postdoc stands at a poster with two panels. Left, their reconstruction with Kashlinsky's filter, there's the dipole. Right, the same data with an alternative filter that better suppresses primary CMB features. The dipole shrinks, then slips within error bars. A senior scientist leans in. So which panel is the universe? The postdoc smiles, tired. The one that survives more ways of being wrong. Here's where it gets important for our river. Even if the dark flow claim fades under Planck's scrutiny, the question it asked was useful. How do we tell local currents from global tilts? Are we mistaking poor subtraction for new physics? The field doubled down on cross-checks. Independent methods, peculiar velocities from distance ladders, density reconstructions from redshift surveys, weak lensing maps, had to line up. If a supposed large-scale flow didn't echo in other tracers, it stayed in the penalty box. While the headlines cooled, our neighborhood map only got sharper. The Dipole Repeller, Shapley tug-of-war handled the observed local group motion in a way the data liked. Laniakea's flow lines, built from real peculiar velocities, drained past the Great Attractor toward deep structure without calling on super-horizon mysteries. You didn't need a cosmic tilt to explain why our arrows pointed where they did. You needed honest accounting, fewer blind spots, and respect for the quiet power of voids. Still, the lure of an edge-of-the-map influence didn't disappear. It moved into cleaner language, constraints. If there's any residual truly large-scale bulk flow, it has to sit under strict limits from Planck baryon acoustic oscillations and the CMB's tiny anisotropies. Theories that once strutted now tiptoe, labeled as speculative. In this game, humility pays rent. Back at the riverbank, you can feel the pivot. Dark flow was a dare. It forced better tools, tougher pipelines, and sharper questions. In the aftermath, what survived wasn't the rumor, it was the discipline. And that discipline points us back to the currents we can weigh, the pushes we can map, and the basin that quietly through the dust, cracking the zone of avoidance. While the debate over pushes and pulls played out, there was still a blindfold over our eyes. The zone of avoidance wasn't a metaphor. It was the Milky Way's midriff, dust, gas, star fields, smearing and swallowing background light across a wide belt of sky. If you rely on optical surveys, you get a map with a bite taken out of it. And when the missing bite sits on the suspected path of our motion, you misread the river. So astronomers turn to wavelengths that don't care about dust. Hydrogen whispers at 21 centimeters. That HI line slips through the murk and tags neutral gas in galaxies you can't see in starlight. Blind radio surveys swept back and forth across the plane, catching spectral spikes that marked hidden systems. Near-infrared light, less mauled by extinction, filled in stellar mass catalogs where optical images looked like static. And X-rays, almost contemptuous of dust, lit up the hot atmospheres of entire clusters, pointing straight at deep wells of gravity. The payoffs came as names we'd ignored for too long. Norma, Able 3627, stared back from the fog, a rich X-ray bright cluster crouched near the plane. The Centaurus wall, a chain of galaxies strung along a filament, ran like a beam behind the dust. Farther along, observers pulled the Vela Supercluster out of confusion, adding weight to a region we'd treated like rumor. Each detection wasn't just a dot, it was a correction to the force field. But seeing through dust isn't as simple as flipping a switch. Extinction corrections are guesses with math. You build maps of how much light is stolen along each line of sight, then you give it back to your galaxies and hope you didn't tip the scale too far. Near the plane, stars pile on stars, source confusion spikes. HI line profiles overlap, foreground hydrogen in our own galaxy smears across the spectrum, and the clean spike you want gets dented by a neighbor you didn't invite. Distances wobble. And when distance wobbles, peculiar velocity wobbles harder. Here, where cross-discipline stubbornness saved the plot. Teams didn't trust any one catalog. They stacked them. A galaxy pinged in HI got a near-infrared counterpart. A cluster with an X-ray halo earned a place in the distance ladder. Peculiar velocities calibrated in the clear sky shifted when the same methods were pushed through the dirty belt. You learned where your biases cracked. Then you folded it all into velocity reconstructions that penalized noise but let structure speak. A micro story from a winter campaign. An observer pulls a night shift at a 21-centimeter survey scanning across the galactic plane. The data look like a picket fence, foreground lines everywhere. Then one fence post is wrong, narrow, receding at a speed that doesn't match Milky Way gas. They tag it. Weeks later, an X-ray catalog shows a hot blob in that direction. The two marks line up. A cluster just off the mid-plane gets upgraded from whisper to shout. On the flow map, a shallow basin deepens and the nearby streamlines nudge. Piece by piece, the caricature of the Great Attractor morphed. Behind the blackout curtain lived not a single beast but a crowd, Norma with its entourage, the Centaurus structures threading through, Vela anchoring a flank. Stack them along our line of sight and you get the impression of a singular pull. Spread them out in distance, and you see a confluence, midstream structure that matters locally but doesn't own the horizon. There was a cultural shift, too. The zone of avoidance had been treated like a permanent scar on our maps, an excuse for why the numbers wouldn't add up. Once radio and infrared made it permeable, that excuse wore out. You could no longer say, "We don't know because dust," without someone replying. Then observe where dust doesn't matter. The cover-up frame landed not as conspiracy but as a reminder. The Milky Way is a bad survey partner if you let it be. Meanwhile, the improved catalog sharpened the boundaries of our basin. Where flows bent around the Centaurus wall, you could draw a line. Where streamlines crossed a shear near Vela, you marked a border. Those borders fed directly into the atlas that would name our home. You could feel it, the way a cartographer must feel tracing a coastline that explorers only guessed at for centuries. One last beat from the fog. An extinction model update nudges brightness corrections by 1/10 of a magnitude across a swath near Norma. Teams rerun distances. A handful of galaxies jump inward. Their peculiar velocities swing from slight recession to slight approach. The local shear eases. An eddy that looked like a separate mini attractor dissolves. You stare at the before and after and realize how thin the line is between a legend and a measurement. With the dust's grip loosened and the hidden scaffolding sketched in, the river's course stopped pretending. The walls and clusters behind the plane didn't end the story. They made it legible. And once the map could move without a blindfold, someone finally drew the orange contour around the true watershed and gave our neighborhood a name. Laniakea, redrawing our cosmic address. Stand back from the tangle and let the river show you the basin. That was the move in 2014, when R. Brent Tully, Hailing Courtois, Yehuda Hoffman, and Daniel Palmer tried something both simple and radical. Define a supercluster not by where matter piles up, but by where motion drains. Instead of counting galaxies and drawing a circle around a dense patch, they traced streamlines, paths a test particle would follow after you subtract the universe's expansion. Where the lines converged, they named a basin of attraction. Where neighboring flows sheared past in opposite directions, they marked a boundary. Then they drew the outer contour that enclosed every flow line headed for our valley. They called that watershed Laniakea, immense heaven. Get this, the map didn't look like the old atlases. It moved. In the Laniakea visualization, individual galaxies sat like bright grains, but the story lived in the white threads. Velocity flow lines turning inward across a region roughly 500 million light-years wide, about 100,000 substantial galaxies pouring toward a gravitational low. And that Great Attractor, we treated like a finish line. In the new framing, it flattened into a saddle in the terrain. Locally flat bottom, yes, with its own sphere of influence, but part of a larger slope that guided streams past and on, trending toward a deeper sink downstream. A human beat from that reveal. Tully stands over a rotating 3D render as the orange contour, the watershed rim, locks into place. He points to a sheer plane where neighboring flows peel the other way. That's a border, he says, not a political line, but a kinematic frontier. On one side, galaxies drain into our basin. On the other, they head for someone else's. The metaphor lands because it's literal enough. This is a cosmic watershed, and we've been living upstream of a much larger valley than our language ever admitted. Meanwhile, the technique did something trust-building. It didn't ask you to believe a single data source. It fused distance ladders, peculiar velocity catalogs, noise-taming reconstructions, all the stubborn tools we've carried through the dust of the zone of avoidance, into a coherent flow field. If a feature depended on one flaky rung, the shear would ripple and the boundary would waver. Features that survived cross-checks earned their coastlines. Laniakea's borders weren't decorative, they were stress-tested. Here's where it tightens our story. Once you accept motion as the organizing principle, the Great Attractor stops being a mythic destination and becomes a navigational hazard, a midstream low that deflects traffic but doesn't claim it. The streamlines, seen in full, keep bending, following filaments through the Centaurus structures, arcing toward the sector where the Shapley Concentration waits. In that sense, Laniakea doesn't trap us, it situates us. It says, this is the catchment where gravity still wins over expansion on these scales, and within this catchment, the long slope leads away from the saddle and down toward the true heavyweight. A micro story from the mapping bench. A graduate student toggles the flow integration step size on their screen. Too coarse and the streamlines jitter, missing the sheer boundaries. Too fine and noise masquerades as eddies. They dial it in, watch two neighboring lines diverge cleanly along a plane that slices the Centaurus wall. That plane is an arc. It's a no-go crossing for flows. On one side, waters feed Laniakea. On the other, they drain elsewhere. The room is quiet because a moving border just drew itself. Meanwhile, language caught up. Supercluster used to mean a crowded patch, and we treated Virgo or Hydra, Centaurus as static regions on a density map. Laniakea reframed the term as a dynamic basin. Within it, the Milky Way and the local group still keep their local contracts. Gravity beats expansion on scales up to the group. But at supercluster scales, expansion tries to pull things apart, and motion toward the attractor valley holds them in a loose, flowing association. It's not a bound city. It's a watershed of towns sharing the same downhill. Then comes the consequence that threads back to our earlier clues. If our basin's floor slopes toward Shapley, then our fate lines trend that way too, modulated by dark energy's push and the filament's forks. The Great Attractor's demotion isn't a snub, it's relief. We named the unknown prematurely. The flow field gave it context. The Dipole Repeller's effective push from one side, Shapley's long pull from the other, and Laniakea's boundaries together told a cleaner story. Our CMB dipole, our peculiar speed, our local shear, they all live inside a moving map that finally admits borders. One last human beat. Helen Courtois describes the atlas as the first map that moves. It's not poetry, it's instruction. Because once you see those lines crossing the orange rim and feel the basin like a real valley under a river, you stop pretending our address is a fixed point under fixed stars. We live on a slope. Our neighborhood has edges. And the stream we're in is already choosing a direction, past the saddle we once mistook for the end, toward the deeper gravity downstream. Shapley, the true heavyweight downstream. Follow the streamlines far enough and the river doesn't whisper anymore. It roars. Downstream of the saddle we called the Great Attractor sits a knot in the web that refuses understatement. The Shapley Concentration, the richest concentration of clusters in our corner of the universe. If our neighborhood's motion has a destination, this is the basin that makes compasses honest. Start with what you can count. Redshift surveys sweep that sector and keep tripping over clusters stacked like cordwood. Able numbers pile up. Spectra put them at similar distances, bound by filaments that lace between them. In X-rays, the map glows. Cluster atmospheres, tens of millions of degrees hot, light up like beacons, each one proof of a deep dark matter well. Weak lensing, galaxies behind Shapley stretched into subtle arcs, adds up the invisible mass without asking it to shine. And when you add it all, the totals are blunt. This isn't a local bump, it's a continental divide. Here's the stakes beat we can feel. If mass is the riverbed, Shapley's is carved deep enough to bend streams across hundreds of millions of light years. Velocity reconstructions that let flow lines speak without editorializing keep steering the arrows that way. In the Laniakea Atlas, threads that once curled into the Great Attractor's flat-bottomed basin now keep sliding, arcing toward Shapley's valley. It isn't just a pretty map. Integrate the flow, and the basin catches traffic. Meanwhile, the data started to say something more specific about our own motion. Take the local group's peculiar velocity budget, how you get from the 600 kilometers per second of our CMB dipole to actual sources. Subtract what nearby walls and clusters behind the zone of avoidance can plausibly provide. Fold in the push from the dipole repellers under density. The remaining vector like Shapley. Different teams, different methods. Peculiar velocity catalogs, Bayesian reconstructions, density to velocity inversions, found their compasses aligning with that basin. A micro story from a lensing group's late night. They stack several cluster fields in the Shapley sector to beat down shape noise. The stacked shear profile rises above the error bars. It doesn't look like a tidy NFW halo. It looks like overlapping halos, filaments, and the connective tissue between them. Someone taps the plot. This is one zip code, they say. We're not measuring a house. We're measuring the neighborhood. Of course, nothing in the cosmic web is a straight road. Between us and Shapley, filaments fork. One path threads through the Centaurus structures we've already met, a corridor of galaxies and groups that feels like an interstate. Another arcs along the longer Perseus, Pisces arm, a different highway running through its own knots and walls. Flow reconstructions can hint at which ramp we've taken, arrows that slightly favor one corridor over the other, but shear planes and local eddies keep the verdict provisional. In some integrations, the traffic merges. In others, it staggers, catching on midstream features before resuming the downhill slide. Complications multiply when you ask how much of our motion Shapley accounts for. Early attempts liked dramatic numbers. Later work got conservative. Under lambdictum, linear theory ties velocity to the gradient of the gravitational potential, modulated by cosmological parameters. In that regime, you can estimate contributions. Local overdensities here, Shapley there. A repeller's underdensity subtracting on the opposite side. Some studies pegged Shapley's share as substantial but not singular, a big piece of the pie, not the whole kitchen. Others emphasize geometry. Even if Shapley's pull is dominant downstream, the path you take around saddles and along filaments decides how cleanly that pull projects onto our measured dipole. But while the number crunching danced, a qualitative truth hardened. The Great Attractor's myth depended on a finish line hidden by dust. Pull the dust curtain back with HI, infrared, and X-rays. Reconstruct the flow with real peculiar velocities. Let voids weigh in with their quiet push. Then follow the streamlines honestly. You end up with Shapley as the true heavyweight downstream. The name matters less than the role. It's the basin your leaves drift toward when they escape local swirls. A human beat from a conference coffee line. Two astronomers trade napkin sketches. One draws the saddle near Norma, a few filaments, a downstream valley. The other draws the same, then adds a subtle bulge off to one side, an intermediate knot that steals attention in some reconstructions.